All right, 3.4, we're continuing to use calculus to give us additional ways to describe the behavior of a function. So in 3.3 we talked about increasing and decreasing functions and finding relative extrema. In 3.4 we're going to talk about concavity, and what we use to describe concavity or tell us more about the concavity is the second derivative. So concave downward looks like this here. And the definition of concave downward is that f prime is decreasing. All right, so one of the things that we have to do in calculus is develop this intuition about what f is doing, what f prime is doing, and what f double prime is doing. And so this is kind of the first time that we've run into thinking about what is happening to f prime. Remember, f prime describes the slope, or it describes the instantaneous rate of change of f. So if we look at this section here, we can think about the slope of this function as we move from left to right. It's steep here. It's as we move across this relative extrema here, we have this concave down section, so we're going to see the slope decreasing, decreasing, decreasing. Now it becomes more and more and more negative. It's still decreasing there. Right? That's the definition of concave down. Concave up, we see that f prime is increasing, which means the instantaneous rate of change is increasing. The slope of this function is increasing. That's the definition of these concave up and concave down. It's kind of a silly way to remember it, but if you read that out loud to yourself a few times, I don't think you'll forget what concavity looks like after that. So the tests for concavity, they're very similar to the tests for increasing and decreasing functions that we used last time with the first derivative, except we're using the second derivative. So we're going to approach it this way. We're going to say, let f be a function whose second derivative exists on some open interval. If the second derivative is greater than 0 for all the x in that interval, then the graph is concave up. And if the second derivative is negative, then the graph is concave down in that interval. Right? So the process that we're going to use is again much like using the first derivative test for increasing and decreasing functions. Here we're going to talk about locate the x values for which f double prime is either equal to 0 or doesn't exist. Use these values to establish test intervals, and then test the sign of the second derivative. All right, so here's our first example that we're going to talk about. Find the open intervals in which the graph, this f of x, is concave upward or downward. So we take a look at this function. We notice that the function itself is continuous on the entire interval from negative infinity to infinity. So we're going to find the second derivative. We're asked to find concavity. We should automatically think second derivative. So we find the first derivative. We take the derivative of that. We have the second derivative. Now, the values that we're concerned here about are when the second derivative is equal to 0. So I set that 3/2 x equal to 0 and solve. I get x equals 0. I also need to think about where f double prime is not defined. Well, it's in this case f double prime is defined everywhere, so we don't have to worry about that. So we only have one x value that we're really concerned with. We're going to use that to set up our table. So our intervals are defined by that second derivative equal to 0. Turns out x is 0, so we have to the left of 0 and to the right of 0. And we have the same type of chart that we made with the first derivative, or using the first derivative. But this time we're using the second derivative. So I choose a test value here. I'm going to try to choose an easy one. Test value is -1 that I chose, because I thought that would be easy. So f double prime of -1, I just plug that into 3/2 times -1. I can see that that's negative, so f double prime is less than 0. The conclusion is f is concave downward. I do the same thing for the other interval. Here I have all the positive numbers, so I can choose x equals 1. I find f double prime of 1. I find that that's positive. So the function is concave upward. So my conclusion is that f is concave downward, on the interval from negative infinity to 0, and f is concave upward on the interval from 0 to positive infinity. Same type of problem, asking us to find the open intervals in which the function is concave upward or downward. So the process is the same. We have a slightly more complicated function here. F is continuous on the entire interval. We find the second derivative. Turns out the second derivative is 2. Right? So it's not really true for me to say this is a more complicated function, because in a lot of ways the cubic is more complicated than a quadratic, but it's a different thing. It's a different function, of course. And then when we get to the second derivative, this is kind of unusual, so this is really why we're talking about this problem. We get f prime of x equals, or f double prime of x equals 2. Well, what do I make of that? I can't set that equal to 0. It's obviously defined, so I can't follow the exact same process, but really what that means is it's actually a really easy problem. F double prime is always positive, so the graph of f of x is always concave up. And of course, if we really had looked at this, taken a second to look at that, we can see that that's just a quadratic. It graphs a parabola, and since the leading coefficient is positive, it's concave upward. So we already knew it was concave upward from Algebra 1 and Algebra 2. But now we can see that through the use of calculus, we get the same result. Now here we have a more complicated function. We want to find the open intervals in which the graph of this rational function is concave upward or downward. Alright, so the process, we're going to first note that f of x is not defined at positive and negative 2. F of x itself has some kind of discontinuity. It looks like a vertical asymptote at positive and negative 2. So we have to include those x values as boundaries for our test. So we're going to find the second derivative. Here the second derivative is a little more work. We have to use the quotient rule. So the first derivative looks something like this. It simplifies out fairly well. Second derivative looks like this. You can see here that I had an x squared minus 4 term here and an x squared minus 4 term here. I could cancel those out with this one down here. That's why I end up with x squared minus 4 to the third here. So I can see by looking at this that the second derivative is never going to be equal to 0. All right. This numerator can never be equal to 0 because I have an x squared here, which will always be either 0 or positive. It's going to be non-negative no matter what my value of x is, and then I'm going to add 4 to it. So I'm never going to get a 0 in that numerator. But I can see that the second derivative is also not defined when x equals positive or negative 2. So that same set of discontinuities shows up again in the second derivative. So as long as I'm careful about really looking at the second derivative, all those discontinuities will show up there. And now, because I have two of those values where f prime of x or f double prime of x is not defined, I have a little bit more complicated table here, and it looks something like this when I get it filled in. Again here, from negative infinity to negative 2, my test value that I chose was negative 3, so I found f double prime of negative 3. Remember what we talked about is in the numerator here. Remember we talked about this numerator can never be negative. So I know that that numerator is positive. So really I just have to think about this denominator. When I plug in -3, I get 9 minus 4, which is 5, and when I cube 5, I get 125, which is obviously positive. So I have a positive here. If I choose a number between -2 and 2, here I chose 0 because that was the easiest one. When I find f double prime of 0, I plug in 0 in here. 0 squared is 0 minus 4. It's a -4 cubed. Gives me a -64. So that's how I know the second derivative is less than 0, and therefore my f is concave down on that interval. And likewise for the interval from 2 to infinity, I used x equals 3. So the conclusion that I come to is that f is concave upward on the intervals from -infinity to -2 and from 2 to infinity, and f is concave downward on the interval from -2 to 2. Sorry about my handwriting. You can see why I have to type out my notes so that you can read them. Hopefully that's somewhat legible and you can figure out what that says. Alright, moving on to the next example.